Hello everyone. Uh, Today I'm going to talk about adversarial search. My name is Jashan Samanaik. So, when we talk about adversarial search, first we should know what is adversarial search. Adversarial search is a key concept in artificial intelligence and game theory where an AI agent analyzes potential moves, also counter moves of multiple players in competitive zero-sum games. In such games, each player aims to maximize their own advantage while minimizing their opponent. The term adversarial indicates that the search algorithm confronts an opponent actively working against the agent's objectives. These algorithms are commonly applied in games like chess, checkers, tic-tac-toe, and various card games where players use strategic moves to compete. Adversarial search also involves addressing the challenges that arise when planning is necessary and other agents are actively strategizing against the current scenario in a game. Multiple players pursue conflicting objectives, navigating through the same search space from the starting state to intermediate stages towards achieving victory. Planning is essential with the assumption that opponents will seek to maximize their own advantage. So next we're going to talk about optimal strategies in adversarial search. In in a typical search problem, the goal is to find a sequence of moves that lead to terminal state, usually winning outcome. However, in a game, both players have a say in the outcome. This means that the player making the first move must consider possible responses from the opponent and plan accordingly. The player who plays first needs to devise a strategy that covers its moves in the initial state as well as its subsequent moves in response to every possible countermoves by the second player, and so forth. Essentially, an optimal strategy in a game ensures that the player achieves outcomes at least as favorable as any other strategy, assuming the opponent plays flawlessly. While finding this optimal strategy is theoretically possible, it's often computationally infeasible, especially in complex games beyond something like tic-tac-toe. So now we're going to move to the next slide. In the next slide, we're going to talk about the minimax algorithm. The minimax algorithm determines the best decisions from the current state by evaluating the maximum values of each possible successor state. This involves computing values for each node in the game tree, starting from the bottom and working upwards. The algorithm employs straightforward approach, directly applying the relevant equations at each step of the recursion. So next we're going to talk about alpha beta pruning. The main issue with minimax search is its exponential time complexity, which grows rapidly with the number of moves in the game. While we cannot completely remove this exponential factor, we can significantly reduce it by employing a technique known as alpha-beta pruning. These methods allow us to compute the optimal minimax decision without exclusively examining every node in the game tree. Alpha-beta pruning allows us to determine the correct minimax decisions without exploring every node in the game tree. It achieves this achievement by employing a form of pruning where certain branches of the tree are terminated based on two threshold parameters, alpha and beta, which guide future exploration. Alpha-beta pruning can be utilized at any depth of the tree and has the capability to not only trim individual leaf nodes but also entire subtrees, thus optimizing the search process further. So, in conclusion, adversarial search presents a challenge and dynamic environment where agents must make decisions while considering the actions of competing with other agents. Through techniques such as evaluating game states, calculating optimal decisions, utilizing search algorithms like alpha-beta pruning, and the minimax algorithm can navigate complex game trees to make strategic choices. The next slide, you can see the references. And thank you for listening to my presentation. Thank you.